Okay, this is the continuation of the previous video. Just gonna discuss a few problems, ray diagrams, lenses. Alright, example, converging lenses. What are the position and the size of the image? 7.6 centimeter high leaf placed 1 meter from a 50 millimeter focal length camera lens. Alright, so let's write down the information we have. DO 1 meter, F it's positive, 50 millimeter means 5 centimeter means, let's keep it as 5 centimeters, let's make this 100 centimeters, which O 7.6 centimeters. Okay, so the diagram says this. Here we have an object, and so that's 100 centimeters, F is 50 millimeters. So what happens is, what is going to happen, let's see how to draw the ray diagram. Light comes in, it's like this, and can take the one that let's say come to the center, goes without bending, so over here it's going to make a small image. Alright, so let's do the math. 1 over DO plus 1 over DI plus 1 over F. 1 over 100 plus 1 over DI equals 1 over 5. 1 over DI over 5 minus 1 over 100. Common denominator 100, 5 times 20 minus 1. We have 19 over 100. So DI is 100 divided by 19. So that's going to be 5 point something. I think, yeah, gives you 5.26 centimeters, the positive number. So the diagram is correct. It's positive for a lens. Positive means it's on the other side, right? Okay. Let's see, that's the position, the size of the image. Let's find the magnification. Negative DI over DO. Negative 5.26 over 100. Negative 0.0526. Yep, so that's the magnification. A very small number means the image is going to be very small. It's negative means it's upside down. That also matches with what we have. It's upside down. So what's the image height? Magnification also equals to HI over HO. So point negative 0.0526 is HI over 7.6. HI equals multiply, let's see what we get. I have 0.399.4 centimeters. That's negative. So a very small image, this diagram is not to the scale. Image has to be much smaller, and so 0.4 centimeters tall, negative, upside down. Alright, so this is a real upside down small image. Let's try another example. An object is placed. Now the previous example is more like a distance object, right? Focal length was what, 5 centimeters. Object was 100 centimeters far away from it. Object placed 10 centimeters from a 15 centimeter converging lens. Converging means convex. F equals 15 centimeters. DO 10 centimeters. Okay, let's draw the ray diagram. Now I'm going to draw the ray diagram first. Try to draw it according to like a somewhat kind of scale. Lens. This is something you need to know, how to draw ray diagrams correctly. So we will do this when we meet in class. Bunch of more ray diagrams. So F on both sides. Object is inside the focal length. So here comes the parallel light, goes through F. Light that goes through the midpoint does not bend. You see that these two lines are diverging, right? They don't meet. We're looking at it from this side. So we extend them backwards. Where they meet here, it makes the image. We have an upright image. Light diverge, so we extend them. So this is going to be a virtual image. Let's try the equation. -30 so this is -1/30, so -30 centimeters. So it's on the other side, it's on the same side as the object, 30 centimeters, which is negative. Magnification. Positive 3. 3 times bigger. For an example, if the object is 1 centimeters tall, image going to be 3 centimeters tall, and it's positive means it's upright. And what else? Negative distance says that it's virtual. Okay. Diverging lens. Where must small insect be placed if 25 centimeter focal length diverging lens is to form a virtual image 20 centimeters from the lens, same side as the object? Let's mark all this on the diagram first. It's a diverging lens. So this type one. Small insect be placed at 25 focal length. So this is 25. Virtual image 20 centimeters from the lens on the same side as the object. So object and image both has to be on the same side. So in general, what kind of images this thing makes? So let's say just generally, right? Let's say you place an object here. Light goes in, diverges such that it's coming from this F. That's one. And the second one, light that goes through the center doesn't change the direction, that continues. So where they meet over here is your image. So this is what we are kind of looking at, right? Focal length is 25. Image has to be 20, so it has to be inside, and this is usually how it happens. It appears inside, so I is. So our diagram kind of looks right to what we are looking at. So let's do the math and try to figure this out. Di plus 1 over. So this is what we don't know. Di. Now it's in the same side as the object. So for an image, that's negative. Negative 1 over 20. This is a diverging lens, so that's also negative 1 over 25. So 1 over d over minus 1 over 20. 25. Negative 1 over 25 plus 1 over 20. 100. Negative 4 plus 5. This is 1 over d over. And going here, 1 over d over equals positive 1 over 100. D over equals 100. You're working with centimeters. This has to be 100 centimeters. Okay. Combinations of lenses. The image formed by the first lens becomes the object for the second lens. The total magnification is the product of the magnification of each lens. Now these are very interesting stuff. You probably, as biology students, very often you use lens combinations. That's what you have in the microscope, combination of lenses. Optical instruments like microscope, telescope, even a magnifying glass, that's a single lens. But microscope and telescope uses multiple lenses, at least two or more. So the way they work, for an example, is, let's say here, principal axis. So here you have one lens. Let's say we are going to use two converging lenses, two convex lenses. Let's say we have an object here. And for this lens, use F and F. So light comes in. Let me use different colors. Comes in, bends. Okay, and that creates an image over here. So what we now do is we take another lens, the second lens, put it over here. So based on where the second lens is and based on where the image is, this object, now this is our actual object, it creates this image over here. This image becomes the object for the second lens. This is lens number 1, this is lens number 2. So then we can start a new set of light. So let's say this one has a different focal length, let's say something like f and f for this lens. So we can start a new set of light. So I'm going to use this color. Light comes parallel, bends. No, what color is a good color? This one. Light that goes to the center. Now it's create an image over here. This first image, this is the image 2 created by second lens. So these are lens combinations, create compact image, like complicated images. The idea is like if it is a microscope, you magnify the image once and then you magnify it again. Multiple magnifications. Telescope, same application. You magnify it once with the first lens, you magnify it again, the second lens, maybe with the third lens. Right? So these are lens combinations. Here's an example. I'll let you all work on this.